I just recall a little bit, explain where we are at this point. All right. Okay. All right. Yeah. So we want to get a new sort, and the new sort should we emphasize on that overall performance. Yeah. In order to do that, when we do divide and conquer, we want to do in a different way, comparing with the quicksort merge sort. We want to do a different way. Yeah. All right. So in this way, in the divide step, yeah. So we need to do, a lot of work, yeah. But at the combine step, we just want to do the trivial combine. Combine step, we want to make it a trivial. So almost do nothing. Yeah, we put things together, we get the whole array sorted immediately. Yeah, so that is our design idea. Yeah. In order to get that, yeah, how can you get a trivial combine, right? Yeah, this is the condition we need. Yeah. If when we have two subarrays, first subarray, second array, if we have this condition, the value of any element in the first subarray is less than or equal to the value of any element in the second subarray, then we have that trivial combine property. Yeah. Because if you sort the first subarray, then you also sort the second subarray, you put them together, yeah, because the largest element in the first subarray should be smaller or equal to the first element in the second subarray. You put them together, the whole array automatically ordered. Yeah, so that observation, yeah, based on that simple observation, yeah. So we know in the divide step, we should get this property at the divide step. Yeah. How? That's another question, right? Yeah. So some of you may think about how to get that. Yeah. That is so hard, right? Yeah. Yeah. So that's the next step, the implementation step. Now let's move to the D.2, partitioning in Quicksort. Yeah. How to do the divide? Yeah. So we need to do partition. We need to get a partition of the original array. Yeah. When we do the partition, we require the maximum of the first subarray should be smaller or equal to the minimum of the second subarray. Yeah. But how to get that at this point? Yeah. You may feel that's very hard. Yeah, that's very hard. Yeah. But there is a very smart method. Yeah. Next we will see there is a, so smart. Yeah. So we want to learn that brilliant idea. Yeah. All right. So let's take a look. Yeah. Yeah. How do you guarantee the maximum of the first subarray is less than or equal to the minimum of the second subarray? Yeah. Because you have no chance to find the maximum of the first subarray, right? And you have no chance to find the minimum of the second subarray. Yeah. Here, the smart idea, we will use we will take very different view. The view is, quite different. Yeah, we change the view. Yeah. All right. Yeah. let's look at it. Look at the solution here. Yeah. The first solution is how to determine two subarrays, right? How to determine two subarrays. Yeah. 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 And we look at it, you know, monitor the time. Yeah. All right. Yeah. That's the first technical question we need to answer. Yeah. How to split? Where is the location to split? Yeah, right? Yeah, because it's uncertain. At this point, it is uncertain, right? So we need to fix that point, that problem. Yeah. Then the next one, you know, maximum of the first subarray is less than or equal to the minimum of second subarray. Okay. So basically, these two questions we need to answer. Yeah. But we can answer together. Yeah. Yeah. At the same time. Yeah. All right. How to split? Yeah. Here. Yeah. The question. Yeah. All right. And at the split time, you cannot do arbitrary split. Because if you do some random split, you won't get this condition. You won't get this condition, okay? Yeah. Yeah. So when you do the split, you need to make sure you have this condition. Okay? Yeah. 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 So then, all right. We need to use a dynamic view. So here, not a static view. So what's that static view? Static view, that means you do the direct split on your data, on your original array. Direct split. Okay? Cut it somewhere in the middle. That's the static view. So what's the dynamic view? Yeah. You can move the elements. Okay? Do not make all the elements static. Stay there. Yeah. You can do an adjustment. You can move your elements around here and there. Okay? Yeah. You can move. Yeah. Treat your elements dynamic. All right? Yeah. You can change the locations of your elements. Yeah. Because it is allowed, right? It is allowed. Yeah. So you use this dynamic view to understand your data. After you make appropriate arrangement, then eventually you get this condition. Okay? Yeah? Yeah. So that's the idea. Yeah. All right. Now let's look at how to make arrangement on all the elements. Yeah. All right. Yeah. Yeah. So here, there is some important, a very important insight on this process. Yeah. Find that insight. Yeah. All right. So when you do the split, you need one special element to separate these two subarrays. That element is critical. Okay? Yeah. So you need to locate some critical element that plays the role as the separator of the two subarrays. Separator. Okay? Yeah. All right. How to get that? So that element must be in place. Okay? Yeah. So that element is in place. You know the meaning of in place, right? Yeah. So that element is at its destination location. Yeah. Then the left-hand side of that element, we use it as the first subarray. The right-hand side subarray of this critical separator element, we use it as the right subarray. So we separate. Okay? And at the same time, we need to have this condition. Okay? So that's the, that's the insight. Yeah. So when you see this, when you understand this idea, then you're almost there. Okay? Yeah. All right. So now we determine the boundary of the two subarrays. The boundary. Yeah. How to determine it? Still another technical question to answer, right? How to determine this boundary, separator element? Yeah. That's another technical question we need to answer. Okay? All right. All right. Yeah. So here, that critical element here, we use this P to represent. Yeah. The P element in place, it separates, it splits the original array into two subarrays. Yeah. This P is in place, all right? Yeah. Then, other elements, so usually not in place. Yeah. Yeah. But this one must be in place. Yeah. So this element, we give a special name for it. We call it pivot element. It's the pivot. So pivot element. All right, so we use the P to represent it. Yeah. So the next question, how do you know which element is the pivot? Right? You cannot just, because we don't know which element must be in place, right? Yeah. You do not have that critical information. You need to determine, there is a cost. You need to do comparisons to determine this pivot element. All right? Yeah. All right. And all the values of the first subarray must be less than or equal to the P value, and all the values of the right subarray elements must be greater or equal to the P value. Yeah. Yeah. So then we have all the requirements satisfied, yeah, but we don't know which element is the pivot. So we need to answer that question. Yeah. All right, next, let's answer that pivot question. Which element is used as the pivot? Okay. All right. Because in the given array, we do not have any information about the values of the elements in a given array, right? Yeah. Yeah. No information. If you have no information, that means any element has an equal chance to be the pivot, right? Yeah. Yeah. We don't know which element has a better chance to be the pivot. Yeah. So all elements, they have the equal chance to be the pivot. Okay. All right? Equal chance. Yeah. If equal chance, that means we can pick anyone to be the pivot, right? Yeah. Yeah. Because no reason to favor any of the element in the given array. No reason. Then let's do the random pick. Okay? Yeah. All right. Yeah. Yeah. So that's the first step, yeah, toward that pivot element. Yeah. 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 Could be random selection. Yeah, no problem. Yeah. Right? Yeah. But another consideration when we pick. Yeah. So the first we look at it from the value perspective. Yeah. From the value perspective, yeah, no reason to favor any element, right? Yeah, that's true. Yeah. But other than the value, there is another important factor in our consideration for the pivot. That is the position consideration. Because the positions for all the elements that are different. Are different. Okay? Some positions are better than the other positions. So position-wise, what do you mean better? Better means more convenient. Some positions, when you use those elements as the pivot element, it's more convenient to work. Yeah. Position-wise, those elements are not equal. Okay? Unequal. Unequal. Yeah. So here, let's see which element has the most convenient position. Yeah. So we want to favor that special element. Yeah. Let's look at the diagram. All right? Yeah. Yeah. And we focus on the positions of these elements. Okay? All right. First, let's consider the position of one element somewhere in the middle. Yeah. If it is convenient, if we use it as the pivot element. Yeah. If we select this element as the pivot, okay, all right, then, because we need to do arrangement, right, rearrangement, okay, move other elements around, okay, from left to right, from right to left. We need to move elements around, okay? But when you do that, it's not convenient, right? Yeah. When you make the move, yeah, it's not convenient. First, this element is not, in general, it's not in place, right? Yeah, because you select arbitrary, random element in the middle. Yeah. Yeah. First, it is not in place in general. If it's not in place, that means at the end, you need to move this element to its destination location, right? Yeah. But for other elements, when you move other elements around, the way to move the elements, you need to do a lot of work. You need to do a lot of work. Okay? Yeah. So that means, so this element looks like a roadblock. Somewhere in the middle, cause some, hard time. Yeah. Hard time on other elements moving around. So that's not convenient. Okay? Yeah. All right. Then, if we, look at other, yeah, so because we don't want the position somewhere in the middle, right? Yeah. So then we look at the position at the two ends of the array. Two ends. Yeah. Okay? Left end, the right end, two ends. Then, no roadblock. Okay? No roadblock, right? Yeah. For other elements, when you move around, you do not need to do any, relative movement based on some element in the middle, right? Yeah. No roadblock. Yeah. You can move freely. Yeah. 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 So this observation tells us these two positions are the best to be the pivot element. Most convenient. Two most convenient positions we should use. Yeah. We just pick one of the two. Okay? We can either pick the left end element or we pick the right end element. Yeah. All right. Yeah. Here in this class, I picked the right end element as the location, as the convenient location for the pivot element. All right. All right. So based on this observation, next, now we can do the remaining rearrangement. Yeah, because we need to have these two inequalities. Okay? Yeah, all right. Yeah. Next, so our goal for the rearrangement of the remaining elements, we want to make all the elements in the A subarray less than or equal to P, and all the values in the B subarrays greater than P. Yeah, yeah, yeah. Because if we put the equal case in the left subarray there, we can remove this equal case. Yeah. For something certain, right? Yeah. Although this place, you know, you have different ways to do it. Yeah. Yeah. You have different ways to do it. Yeah. Here we just pick a, you know, relatively simple way. Yeah. Yeah. So we can leave all the elements that are equal to P to the left subarray. There, the right subarray, P strictly less than the values of all the elements in the B subarray. Yeah. All right. Now, based on this picture, you can see it's not very hard to complete the remaining steps in this partition step. Yeah. All right. D.3, implementation of the partitioning step. Okay. All right. Yeah. Straightforward implementation. Yeah. When I talk about implementation, yeah. So I want to, you know, first I need to give you a special concept. Yeah. Special concept. Yeah. All right. So here, what's the consideration? Yeah. When we design algorithms, we want to design an efficient algorithm, right? Yeah. But when you talk about efficiency, what are the main consideration factors when you talk about efficiency of an algorithm? What are the main factors to be considered? Yeah. Here, two main factors in our consideration. Okay, all right. Regarding the, you know, overall efficiency. Yeah. All right. Overall efficiency. The first factor, number of comparisons, right? Yeah. All right. The second factor, yeah. Yeah. We didn't talk about it much before, yeah, but here I need to point it out. It is also important, okay? Also important. That is the amount of space used. Okay? Space used. Okay? Yeah? Yeah, implementation. And the first consideration, it is the primary consideration. The second consideration is this secondary consideration. Not as important as the first one, yeah, but it's second important. Okay? The first one is the most important. The second one is the second important. Yeah. Also important, yeah, yeah. All right. And here in this place, yeah, we need to also try our best to reduce the space used for our data storage. Okay. Yeah. Thus, amount of space used, we want to minimize the amount of space used in our implementation of the partition step. Okay? Yeah. That's also important. Now, so let me look at that. The straightforward implementation in our first try, we ignore this. Okay? Yeah. The first try, we ignore it. Okay? Yeah. Yeah. Our second try, then we add. We try to do better in space part. Yeah. First, we don't worry about the space. We just want to get it done. Yeah. Get it done. Yeah. Without worrying about space used. Yeah. All right. Now, in this diagram, let's do the partitioning. Okay? Yeah. All right. Diagram. Yeah. Let us scan this array from left to right, from beginning to end. Yeah. Every time when we process the current element, yeah, so we compare the current element with the pivot element, right? Yeah, because the pivot element is used as the separator. So we do comparison. All the other elements, we should compare them with this pivot element. Where an element is less than or equal to the pivot, then we drop it to the first subarray. Where the value of the current element is strictly greater than that P, we drop it to the second subarray, right? In that way, after one scan, we complete the separation, right? Yeah. So all the elements less than or equal to P all belong to the first subarray. All the elements that are strictly greater than P all belong to the second subarray. Then we're done. Okay? Yeah. The partition step is done. Yeah. So easy. Yeah. So easy. Yeah. All right. Yeah. But there is one problem. One problem. We cannot ignore. Yeah. The space problem. How much space is used in this way? Because if you do in this way, you need to use two auxiliary arrays, right? Yeah. Two auxiliary arrays. That's the extra space you need to use, right? Yeah. Auxiliary, you need to allocate new storage resource to these two auxiliary subarrays. Yeah. That's the, that you use a lot of space. Yeah. And you want to improve that. Yeah. Too much extra space used. Yeah. All right? Yeah. Yeah. All right. The ideal situation is yeah, because in order to get the best efficiency, yeah, because the more, yeah, think about. So here the reason why we try to save as much space as possible. The reason is the storage space in main memory is limited, right? Yeah. The storage space in main memory is limited. If your algorithms use too much memory resource, then your algorithm will be slow down. Okay? The more memory space you use, the slower your algorithm. Yeah. Okay? Yeah. So if you can use, if you can save as much space as possible, then you can improve the overall performance. Yeah. So that's another factor. Okay? Yeah. Here, we want to eliminate auxiliary subarrays. Yeah. Without using auxiliary subarrays, can you still make the partition? Yeah. That's a little challenging. That's a little challenging, but worth the effort. Yeah. So you want to do it to save more memory space. Okay, all right. Yeah. Next, we want to eliminate the extra space used by these two auxiliary subarrays. Yeah. All right. Yeah. Yeah. All right. How to eliminate it? Yeah. So how to eliminate it? Yeah. All right. Yeah. Yeah. So here, yeah. Let us focus on. We want to control extra space used. Okay. Yeah. All right. Yeah. We can use. Yeah. It does not mean you're not allowed to use extra space. No. You're allowed to use extra space, but when you use the extra space, you should use as little as possible. Okay? Not use too much. Yeah. So here, another question. You may ask me, what do you mean extra space, right? What do you mean extra space? Yeah, here, let me give you the explicit meaning of the extra space. Extra space means the space other than, yeah, because, yeah, what is the space? Normal space, not extra space. Okay? Normal space. Yeah. Yeah. So the storage space used space for input and output. Okay? Input and output. Yeah. Yeah. Because you always need to store input and output, right? Yeah. So that's the normal. That we do not treat it as extra. Okay? Yeah. Normal space. Not extra. Yeah. Then, other than the normal space, yeah, the extra added, yeah, that's the extra space. Okay? All right. So you want to reduce that extra space. Okay? All right. Yeah. All right. So here, how to control, let me describe the idea to control extra space. All right. Yeah? We manage all the elements other than the pivot. Yeah? All those elements we manage. So we use different regions to describe the status of those elements. Status. Okay? All right. The first region, we use this S region, yeah, because it refers to smaller than P. Okay? Smaller or equal to S. Okay? Smaller. Okay? Yeah. Or equal. Okay? All right. L larger. Okay? Yeah. L larger, greater than P. Okay? Yeah. All right. So for all the elements after we do comparisons with P, if they are smaller or equal to P, yeah, we put them in the S region. When we do the comparison with P, if we find they are greater than, they are larger than P, we put them in the L region. Okay? Yeah. And when we scan the original array, we grow this S region, and we also grow the L region, right? Eventually, S region, L region cover the whole array except P. Then we're done, right? Yeah. At the end, yeah, the first subarray corresponds to the S region. The second subarray corresponds to the L region. Okay? Yeah. Then we are done. Yeah. Yeah. So you can see. Yeah. But we also need a third region, U region. it refers to unprocessed. Yeah? Because some elements, before we do the comparisons, they are unprocessed, right? Yeah. So we also, because we need to cover all the elements other than P. Yeah. So we need to manage these three subregions, three regions. Yeah. All right. All right. Then, in A subarray, yeah, when we start, yeah, so at the beginning, our S region is empty, right? L region also empty at the beginning. Yeah. Nothing, no element in each of the two regions. Yeah. All the elements other than P are in the U region. Yeah. Then we do comparison one by one to grow S region, to grow L region. Yeah. All right. Yeah. Yeah. And eventually, the U region becomes empty. Then we are done. Okay. Yeah. So that's simple. Yeah. All right. Next, I want to use a concrete example to show you the partitioning details. Okay? After you see, yeah. Remember our question number 11 in homework, number 11 of homework assignment 2B, that's based on this example. Okay? After this example, after you understand the details, then you just do the same thing on the array given in question number 11, then you're done. Okay? Yeah. So that's why I said after today's class, it's very easy to answer question number 11 in homework assignment. Okay. All right, let's do a simple example here. Yeah. Here, I use this array as the simple example. Okay? All right. Then we start step by step, one by one. Yeah. We pick the last element as the pivot element. Okay? Yeah, last one, pivot element. All right. So U region, yeah, we use different colors to mark different regions. Yeah. U region, we just use the white color. Okay? Unprocessed, white color. Yeah. All right. Then we need the extra space because we need to do swap operation. When you do swap, you need extra space, right? Yeah. Yeah. But here, the swap, we only need one position for the swap operation. Okay? All right. Yeah. Now, let's do the scan from beginning to end. Yeah. One by one, processing. Yeah. All right. Yeah. Let me show you the details here. Well, now, when we start, we initialize. Yeah. S region empty, L region also empty. Yeah. All right. Then our first comparison, we compare the first element 2 with the pivot element 4, and we see 2 is less than 4, so it should go to the S region. So we grow S region 2, and we use yellow color to represent elements in the S region. Yeah, all right. Second comparison, next element 8, it is greater than 4, so it should go to the L region. Yeah, we use green color to mark the elements in the L region. Yeah. All right? Yeah. So pretty simple, right? Yeah. Comparison number 3, 7 and 4. 7 should be placed in L region. Yeah. So we color it in green. Yeah. Very easy, simple. All right. The next comparison, compare 1 with 4, and 1 should go to S region, and we color it in yellow. Yeah. But after this step, you can see these two elements in the yellow region, they are separated by the green elements. That's not good. Yeah. Because based on our understanding, all the yellow elements must occupy consecutive locations. They should not be separated. Okay? Yeah. So we need to fix that. The separation problem should be fixed. The question, how to fix this separation problem? Yeah. Can we use a swap operation? Remember, we are allowed to do a swap operation, right? Can we use a swap operation to fix this separation problem, right? Yeah, yeah, yes. Yeah. Think about if we just swap these two elements, element 8 and element 1, we swap these two elements, then we fix that separation problem, right? Yeah. After the swap, you can see, yeah, two yellow elements occupy consecutive locations. Okay? Yeah. The problem solved. Yeah. All right. Let's keep going. Compare element 3 and 4. Element 3 should be placed in the S region, and we need another swap to fix the separation problem, right? Yeah. So another swap between 7 and 3. Yeah. After the second swap, we fix that separation problem. Okay? Yeah. All right. The last element, 5, is greater than 4. Yeah. So we just put it in the green region naturally, right? Yeah. Then the last step, yeah. Because the last step, the pivot element should go to its place, its right position. Yeah. Put it in place, the pivot element. Yeah. So we need another swap to put a pivot element in place. Yeah. Let's swap element 8 and 4. After this final swap, then we complete the partition step. Okay? Yeah. So the pivot element separates two subarrays, and these two subarrays have the required condition, right? Yeah. Yeah. All the elements in the first subarray are less than or equal to the pivot element, and all the elements in the second subarray are greater than the pivot element. Then we complete the partition step. Okay? Yeah? Yeah. And this is just the one typical partition step. Yeah. And we can apply this partition step recursively. Yeah. Every time when we need to work on the current array, we apply this partition step. Okay? Yeah. All right. Yeah. Recursion, and then by recursion, we complete the whole sort, right? Yeah. Whole sort is done. Yeah. If we can do our partition step like this, then the whole sort can be done in this way. Yeah. All right. Yeah. Now, we need to do some analysis. Yeah. Yeah. Efficiency analysis. Yeah. All right. Oh, before we go to the efficiency analysis, yeah. So follow this example to work on question number 11, okay, of homework assignment 2B. Yeah. Okay. All right. Yeah. Follow the steps here. Yeah. 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 I think it's relatively easy, right? Comparing with other questions. Yeah. So this question, yeah, is relatively easy. Yeah. All right. Yeah. Next, yeah. How to control S region and L region? Not hard. Yeah. Not hard. Pretty straightforward. Yeah. So we use two index variables to control. Yeah, all right. I index variable and a j index variable to control these two regions. Yeah. S region, we use indices from 0 through I, yeah, the elements with these indices. Yeah. L region, we use indices from I plus 1 through j. Okay? Yeah. Then the remaining in the U region. Yeah, all right. Then, yeah, we grow S region and we grow L region. Okay? Yeah. So we just change value of I and the value of j. Yeah. All right. When we grow S region, grow L region, after we swap two elements, yeah. So you can see, yeah, yeah. I value is incremented, right? And j value incremented. Okay? Yeah. So easy to control. Okay? Yeah. Yeah. All right? Yeah. Yeah. All right. Next, worst case efficiency. Yeah. Worst case efficiency. Yeah. All right. The quicksort. Yeah. Yeah. Our focus is on the overall efficiency. That is the average case. Average case efficiency, we use it for the overall average case. We use it for the overall efficiency. Yeah. So we want the average case efficiency as fast as possible. Yeah. But we need to sacrifice a little bit. Yeah. We cannot get everything. So we need to sacrifice a little bit. So the sacrifice is at the worst case part. The worst case is very bad. The worst case is very bad. Yeah. Yeah. But the good thing is the percentage of the worst case is very small. Yeah. So we just take it. Yeah. Percentage. Yeah. Yeah. Very small. Yeah. 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 So if we apply this quicksort many times, the overall performance not, very good. Yeah. All right. Yeah. Let's look at the worst case. Under what situation we get a worst case? All right. Yeah. The worst case happens when the partition is extremely unbalanced. Yeah. So this unbalanced. Yeah. When you split two subarrays, unbalanced, extremely unbalanced. So, in what situation you get an extremely unbalanced split? Yeah. Two extreme cases. Okay? Yeah. It's very easy to see two extreme cases. First extreme case, your L region is empty. Okay? All the elements other than P belong to the S region in yellow color here. Okay? That's the first extreme unbalanced case. All right. The second extreme unbalanced case, all the elements other than P belong to the L region and the S region is empty. Yeah. Another unbalanced case. Yeah. If you always get these two, one of the two extreme unbalanced cases, eventually you will get the worst case. At the end, you will get the worst case. Okay? That's simple. Yeah. All right. Now, we can calculate the number of comparisons on this, on the, for the worst case. Yeah. And for both of these cases, we need to use n-1 comparisons, right? Yeah. Yeah. Because we need to compare all the elements other than P with P. Yeah. So there are n-1 elements other than P, so we need to do n-1 comparisons. Yeah. But after n-1 comparisons, what is the problem size reduction? The problem size reduction is you only reduce the problem size by 1. Reduction by 1. Then the reduction is too slow. Every time you reduce the problem size just by 1, okay? Yeah. It's too slow, all right? Yeah. Yeah. So now when we calculate, equally bad. Yeah. If you look at that, so here for this question, if you look at from the comparison point of view, equally bad, right? But there is a small difference. If you look at from the swab point of view, yeah, one is worse than the other. Okay? Yeah, yeah, yeah. You know, this green one is worse. Yeah, because you need to put a P element in place, right? Right? You need to put P element. And the yellow case, P is already in place. You do not need to do any swap. Yeah. So slightly different. If you compare the swap operation, these two extreme cases, slightly different. Yeah. All right? Yeah. All right. Then, let's look at the whole worst case, including the recurrence relation from beginning to end. How many comparisons we need? Yeah. That's very easy to calculate. Yeah. You know, the number of comparisons. Yeah. All right. Yeah. So the recurrence relation like this, yeah, because every time after we use n-1 comparisons, we only reduce the problem size by 1. The size reduction is very slow. Yeah. All right. So then we add up all the comparisons going through all size reduction steps, yeah, because we need to do 1 plus 2 to n minus 1. Okay? Yeah. So we get 1/2 times n minus 1. That's pretty bad. Yeah. The worst case efficiency of the quicksort is very bad. Okay? Yeah. All right. The good thing is, because it occurs in a very small percentage. Okay? The probability is very small. Okay? So when we do the average, yeah, so the impact is also very small. Okay? Yeah. All right. So we do not worry about it. Yeah. So we can use this algorithm. Yeah. All right. So then, yeah, so here, give you some idea about the overall performance of quicksort. Yeah. The quicksort is faster than all the other sorts. Yeah. How do you know that? Yeah. So if the average case efficiency, yeah, here, let me give you average case efficiency. It is big O of n log n. Big O of n log n. Yeah. Yeah. How to see it? The analysis part, very complicated. Yeah. So we cannot do the rigorous math here. You know. Yeah. All right. Yeah. But the average case here in the same level as the merge sort. Merge sort merge sort, we have the also this, yeah, merge sort, best case, worst case, average case, all in this one for merge sort. Then, how do you know quicksort is better than merge sort, right? If you look at the asymptotic notations, yeah, their average case all in this category, same category. Yeah. How people know quicksort is faster than the merge sort? Yeah. Do experiments. Yeah. People so give a random array, the same random array, you know. You apply quicksort here, merge sort there. Yeah. So you clock the response time. Yeah. But you need to do many, many times. Yeah. One experiment is not enough. Okay? Yeah. Do large number of times. Then you take average. You can compare. Yeah. Quicksort is faster than, you know, all the other sorts. People know. Okay? All right. Yeah. Yeah. All right. Yeah. All right. Yeah. So then, yeah, for the worst case example, yeah, so we can, you know, imagine any different type of worst case. Yeah, yeah, yeah. Here you can see, yeah, oh, sorry, yeah, yeah. Here I use just some simple examples to show you a few worst case. Yeah, yeah, all right, yeah, yeah, all right. But then we know people want to avoid the worst case. Here you can see, yeah, these two cases will cause the worst case. One, when the array is in ascending order, that's, yeah, ascending order, okay? Okay, ascending order. Or another is descending order, okay? Descending order. Both cases corresponds to worst case. Quicksort. Yeah? Yeah. Because you hit that, you know, these two extremo cases, right? Yeah. Yeah. So every time when you run partition, you get one of the two extremo cases. So, yeah. So the input like, so worst case. Yeah. So because the ascending order, descending order input could happen, right? Yeah, could happen. Although the percentage may not be high, it could happen. Yeah. So you may want to do something different to break these two cases. If you do not do anything special, then you get these two worst cases. Yeah. But you can do a little easy step to break these two cases. Yeah. Yeah. So let me talk about sometime later. Yeah. Today, let me before the end of class, let me say something about the best case efficiency. Okay, yeah. So we finish this best case efficiency. How to get the best case? Yeah. Okay, the best case, you know, much faster than all the other case than the worst case, right? Yeah, and faster than all the other cases. Yeah. So, on the worst situation, you get the best case. Yeah. So based on our understanding, when the data has the most balanced partitioning, then you get the best case. Yeah. Balancing principle. When you split your data in the most balanced way, you will get the best result. That's our partitioning balancing principle. That's our balancing principle. Okay? Yeah? All right. So here we consider the even split. Every time, when you apply the partition step, you get an even split for these two subarrays. Then, if you can always get the most balanced split at the end, you will get the best case efficiency. Okay? Yeah. All right. Then, even split corresponds to this recurrence relation. Okay? Yeah. Yeah. So, to do the analysis, we need to estimate on this recurrence relation. How to estimate? Yeah. So I mentioned a little bit in the merge sort. Yeah. At that time, I said in the quicksort, I would do it again. So here we need to do it. We need to draw a recurrence tree to estimate this t function. Yeah. Here, let me quickly go through the recurrence trees method here. Okay? All right. Yeah. So how to construct recurrence tree? Yeah. Here. Because in the recurrence tree, we have levels, right? Tree levels from top to bottom, many tree levels. So we need to, in order to control the number of levels, we need to consider n is in 2 adjacent power of 2. Yeah. These two numbers, they are 2 adjacent power of 2. Yeah. N is between. We need to identify which interval of 2 adjacent power of 2 contains this n. Yeah. Then we can determine the number of levels in the recurrence tree. Okay? All right. Yeah. So here we estimate. Yeah. 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 Because this represents the data size. Data size. When the data size is between 1/2 and 1, then we hit the bottom, right? Yeah. We hit the bottom. Okay? Recurrence tree. Yeah. When we spread, when we're going down from top to bottom, the size, data size of each subarray becomes smaller and smaller. At the end, the size is so small, it is less than 1. We can stop. Okay? Yeah, so that idea. Yeah, all right. Then, yeah, so this is the recurrence tree. In the recurrence tree, we only store or write the non-recursion term. This Cn is the non-recursion term. This is the recursion term. Okay, recursion term we do not need to write. Yeah, because eventually recursion term after recursion, all disappear. Okay, yeah, but the non-recursion terms all remain. Okay, when we do the split, yeah, all non-recursion terms all stay. Yeah. So all right. Yeah. So let me finish quickly. Yeah. So then at the end we accumulate all the non-recursion cost. We will get a total cost. Okay. All right. But each level non-recursion cost is Cn. So you accumulate each level also Cn. Okay. Each level, if you combine all the non-recursion terms, you get a Cn. But how many levels? K levels, right? K, we can use log n to estimate K. So the total non-recursion cost accumulated big theta of n log n. Yeah. That's the best case of the quicksort. The best case. Yeah, not the worst case. The best case. Yeah, best case, this. Yeah. All right? Most balanced split. Yeah. All right. Yeah. Yeah. Average case, yeah, too hard to do the analysis. Okay, yeah, because hard to control, too hard. So we cannot see the analysis, average case analysis for the quicksort. Yeah, hard to control. So people can only do experiments for the average case. Yeah, so experiment for the average case. All right, yeah, but it's still, because it cannot be better than the best case, right? Yeah, it is worse than the best case. Yeah, but not too much worse. Not too much worse. Okay. Yeah. So we still have n log n. Yeah. All right. So let me stop right here. Yeah. So the remaining some comments. Yeah. So I can leave it next time. And next time I use 5 minutes to complete the comments. Yeah. All right. Yeah. So we can say we finished module 4. Yeah. So next week, the first class we do module 5. I just give you some interesting view. Yeah. But after that, second class we do review for the final. Okay. All right. Yeah. So keep an eye on my announcement. Yeah, because I plan to give. Yes.
When is the final? When are the final exams going to start? Is it going to be next week? The final exams?
Not next week.
Oh, next
Another week. December 18th, Thursday. December 18th. 2 weeks from today. 2 weeks, not 1 week. Okay.
So the week after next week is going to be our finals week at UMSL, right?
Correct.
Oh, thank you, Professor
Correct.
Lee.
Yeah.
I hope you have a great weekend.
Okay. Yeah.
Snow day didn't
Right. Yeah.
car or driveway or anything.
Yeah. Keep an eye canvas, because I may extend your deadline 1 or 2 days for the second homework assignment. Okay?
Thank you, Professor.
Yeah.
Have a great weekend.
Yeah. You too. Yeah. All right. That's it.